Greetings, physics enthusiasts. Welcome to AP Physics 1, Unit 6, Lesson 1. And as you are aware, the unit does not necessarily correspond to the chapter number. So this unit corresponds to the chapter in the book that I'm currently using, chapter 13. So if you're using the book that I'm currently using, chapter 13. And this is our first lecture on this unit. And the unit is about waves and then this SHM, that stands for something. And I'm not going to talk about it today. So that's something exciting for you to find out if you read ahead in the book, read chapter 13, or just wait for me to talk about it in a subsequent video. Today, I'm going to talk about waves. And I love it. One of my favorite things is when we're doing science and there's a word and I realize, they use that same word outside of our very specific little science world. Maybe they use it in general conversation. Maybe they use it in English class. Maybe they use it in history class. Maybe they use it in art class. So I'm always interested in how the word is used outside of science, outside of physics. And then maybe it's just a different use of the word, but maybe the way they use it somewhere else illuminates and lets us know what's going on. So I like to ask people when we're together in person, what do you think of when you hear the word wave? And since we're not in person, I will just list a few things that people might think of. They might think of waving hello. I'm waving hello. And it turns out that as we study waves, there is something very similar to all of the physics that we're thinking about in waving hello. How cool is that? Some of you might have recently traveled to the beach. Maybe it was the weekend and you had some time and you drove to the beach and you noticed that the water came in and the water went out. The water came in and the water went out. And those are waves. So there's beach waves. And so I wonder if there's something that relates there. Yes, there is. Now, when I say beach waves, there's actually a hairstyle called beach waves. I have very, 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 very straight hair. In fact, you could get a curling iron and curl my hair, and then I could just run a comb through it one time and boom, it'd be stick straight again. But unlike my hair, there are people who have curly or wavy hair. Is there something similar to that wavy hair to what we mean in physics when we say waves? Yes, absolutely. I'm not telling you what it is yet. And then, of course, maybe even among the silliest of the things that you could think of, has anyone ever been to a baseball game at Dodger Stadium and they do the wave? And when we do the wave, there's tens of, maybe not tens of thousands, there's a lot of people, there's probably thousands of people at the stadium. And all the people in section A stand up. And then they sit down, and then all the people in section B stand up, and then they sit down, and then all the people in section C stand up and they sit down. And it makes this wave of people go all the way around the stadium. And so maybe you would call it the wave, or maybe you would call that a stadium wave. But I bet, and I hope that you've had an opportunity to participate in this because it's just fun. It's the most fun thing for me about going to a baseball game because I don't really like baseball that much. Anyway, but so I like the wave though, and I like the food. I love the nachos. Anyway, so this stadium wave is super fun. If you have no clue what I'm talking about, click pause, go to YouTube, and Google baseball stadium wave, and I bet there will be an example of people doing that. And it's really fun. It looks like there's this wave. Okay, I'm going to have one more example. Amber waves of grain. So there's a song that they sometimes sing at the baseball park, and it contains this phrase, amber waves of grain. And some of you, because you didn't grow up in an agricultural community, have no idea what that means. So amber is kind of a pretty goldish brown color, and grain is grass that grows. So if I have a whole field of grass and the wind blows across that grass, it looks like there's this wave, this bouncing, slithering thing that goes across the field. And a very poetic way of describing that would be amber waves of grain. So anyway, this beautiful wave traveling across space. So what is a wave? Some of you might have come up with sine waves or cosine waves. So many examples. So what I'm going to do right now is I'm going to show you an example of a real physics wave on a slinky. So we're going to have to turn my computer around here. Not, I am still here. I'm still here. Wait, we're looking at, I don't have to turn the computer around. I can just turn the camera. Ta-da. There's my classroom. Okay. And I want to be able to see this little slinky down here. Do you see that little slinky? Oops, that's tilted. Anyway, there we go. Now you can see the slinky. And let's see. I want you to see as much of it as possible. There we go. That's going to work just fine. So I'm going to show you a wave with the slinky. Can you still see me? Can you still hear me? This often works best with multiple people, but I'm alone here. So the other end of the slinky is held by a chair on the ground. I can, isn't that beautiful? Did you see the wave move along the slinky? So there's one way of doing a wave like this. This is a continuous wave. Continuous wave. That's not as important as what I'm about to show you now, a pulse wave. Boom. The pulse is just the one little bump. Pulse. If I make the slinky tighter, you'll probably notice that the pulse travels faster. I could do this all day. Now I'm going to change it. Look at this way. Okay, so that's my wave demonstration. And of course, I hope you were able to hear what I was saying. If not, I will share that audio with you via another modality. So we also have our slinky wave. I think the slinky toy is spelled S-L-I-N-K-Y. So all different kinds of waves. What I'd like to do now is talk about the stadium wave, which I hope you're familiar with, and give you some wave vocabulary as demonstrated by the stadium wave. What moves around the stadium? Think about that. What moves around the stadium? Well, the wave moves around the stadium. But is there anything, is there any matter that moves around the stadium? There's really no matter that moves around the stadium. We could say the wave, or we could call it the disturbance. We call it a disturbance because people are sitting in their seat and then all of a sudden, they stand up. They're disturbed or displaced from the equilibrium they originally found themselves in. So the wave moves around the stadium, or the disturbance moves around the stadium. Or we could say energy moves around the stadium. Three different answers to that first very important question. What moves around the stadium? Now, think about that in the slinky wave that you just observed. Did any metal travel from one end of the slinky to the other? Did the metal start at one end and end up at the other? No. Did the individual coil of the slinky travel from one end to the other? No. Every coil that was on one end started and ended at that end. All the coils in the middle stayed in the middle. All the coils at the other end stayed at the other end. But if you think about it, the slinky started out looking like this. And then there was a moment when the slinky looked like this. So these coils were disturbed from their equilibrium. And then a moment later, it was these coils that were disturbed. And a moment later, it was these coils that were disturbed. And then a moment later, it was these coils that were disturbed. So the disturbance moved from here to here to here to here to here to here. The disturbance moved along the slinky, just like in the stadium wave, the disturbance, but not people, moved around the stadium. And similarly, there's energy that starts here that travels along the slinky. So truly, energy moves along a wave. We have a special name in physics for this motion. So instead of saying what moves, oh, here's a fancy word, I could say what propagates. Propagates. What propagates around the stadium. So the word propagation is another word for motion. I'm just making sure I spelled that right. I think I did. Good. So propagation or transmission or motion, all synonyms. Now, here's another great question that's going to lead to some fun vocabulary. What does the wave travel through? What thing, what material, what substance does the wave travel through? Well, for the slinky, the wave travels through the slinky, or the wave travels through metal. For the stadium wave, the wave travels through people. People are the thing through which the wave travels. For sound, if I whistle, that sound travels through air, unless you're a dolphin or a whale, in which case that sound travels through water. Now, we have a name for this substance that the wave travels through. It's called the medium. M-E-D-I-U-M. So the medium is the thing through which a wave travels. So air is a medium for a sound wave, unless you're a fish or a whale or a dolphin, in which case water is the medium. If we're talking about the slinky wave, metal was the medium. If you're at a Dodger game, people are the medium. This is one of those words that I love to think about in other academic disciplines. Art is an academic discipline, and we use the word medium in art class. Some artists use watercolor as their medium when they paint. Other artists use ceramics as their medium as they sculpt. And remember, an artist doesn't just make something pretty that makes you happy. The idea of art, I think, you can ask one of your art teachers to confirm this. The idea of art is that the artist has an idea or an emotion or a feeling or a mood or something in their or her or his head. that they or she or he wish to communicate, to transfer over into your head. There's something in the artist's head that the artist wants to be in your head. And that transfer happens through, via, by way of the medium. Just like I've got energy here, I want the energy there. So the energy travels through, via, by way of the medium, which in this case is metal or the slinky. So that word medium is used in the same way in the academic discipline of art as it is used in the academic discipline physics. That excites me and makes me very happy. So, so there we go. Propagation is an important word, and medium is an important word. And so I hope by now you're starting to realize, okay, so a wave is something that travels, energy is traveling, it's traveling through something, and then there's this disturbance that things are at rest, at equilibrium, but then there's a moment when they're not. And then they go back to equilibrium and the next thing is disturbed. And then they go back to equilibrium and then the next part is disturbed. And then they go back to equilibrium and then the next part is disturbed. So one way of drawing a wave is the way we end up drawing it in your math class a lot. It ends up looking like this. And I know this looks like a sine wave or a cosine wave, and I'm not going to define sine and cosine for you because you've already talked about that in your math class. But there are some different parts here on the wave that I'm going to name for you ever so briefly. The top part here or here or here, the place where we are maximally displaced in one direction, that's called the crest. This is a crest, this is a crest, this is a crest. These places down here where we are maximally displaced or disturbed in the other direction are called troughs. Each one, this is a trough, this is a trough, this is a trough, together they are troughs. The wave had this equilibrium location, and then this part was disturbed, then this part was disturbed, and so on. So we have a crest and a trough. Now there is a maximum displacement here from equilibrium. So this distance or this distance, and it should remain constant there. Any of these distances I could call capital A, capital A, capital A, capital A. A stands for what we call amplitude. The maximum distance that a particle is disturbed from equilibrium. And I'm just going to say a common misconception is that this is the amplitude. No, it is not. From crest to where trough would be is not amplitude. This is twice the amplitude. The amplitude is from equilibrium down to a trough, or from equilibrium up to a crest. From crest to trough is twice the amplitude. So be sure you don't ever fall for that. All right. And then this distance from crest to next crest, or from trough to next trough, that's called the wavelength. And I'll write it again, wavelength, but I'm going to use the abbreviation. Do you think we might use a W for wavelength? That would make sense, but we don't. We use this Greek letter lambda. It's spelled L-A-M-B-D-A. So if the wavelength is 30 centimeters, if this is 30 centimeters long, I would say lambda equals 30 centimeters, that distance. Lambda is a letter in the Greek alphabet. It probably makes the L sound, just like the letter L. So wavelength, we use lambda. So it kind of makes sense. All right. Now, the last thing I want to show you in today's talk, and we have plenty of time, good. I'm not droning on too much. I want to draw for you what the slinky looked like at the beginning. That's what the slinky looked like at the beginning. And then I sent a wave through the slinky. So it looked like this. And then a moment later, it looked like this, right? And then a moment later, it looked like this, right? So as the wave propagated along. So we could say this coil, a moment after we began, was displaced, and then it went back to where it started. So we could look at an individual coil. It got displaced from equilibrium, and then it went back. And what I want you to compare is this direction, which we call the direction of propagation. The energy travels from left to right across the page. But did this individual coil ever travel left, right? No, this individual coil moved up and down. So for this wave, the direction of propagation and the direction of displacement of the matter were perpendicular to each other. Do you see this? Left, right, up, down. And so one word for perpendicular is transverse. So this is an example of what we call a transverse wave, where the direction of propagation is perpendicular to the back and forth motion of this little coil, of this little particle of the medium. Now, let's contrast that. Didn't I draw, let's see, I'm going to draw the slinky again before we send the wave. Remember, I showed you a different kind of wave where instead of going like this with the slinky, I pulled some coils back and then I let go. And what that did is none of the particles went up and down like this. There was just a kind of a darkness that traveled along the slinky. Did you notice that? And you can rewind and watch that part again. But the slinky had some coils that were bunched up. And then a moment later, the bunched up coils were there. And then a moment later, the bunched up coils were there. So this region of compression, again, propagates. I still have the same direction of propagation. But an individual coil started here. And then what happened is that individual coil got pushed over here, and then it moved back over here. So an individual coil got displaced back and forth like this, as opposed to an individual coil getting displaced back and forth like this. Back and forth is a great word. This propagation and this propagation are both in the same direction. But this back and forth and this back and forth are not. This back and forth is kind of in the same direction as propagation. We've got propagation and I've got back and forth. P-R-O-P-A-G-A-T-I-O-N. Back and forth. I'm going to abbreviate that and call it to and fro. That's kind of an old-fashioned way of talking. And so these are in the same direction. We call this longitudinal, L-O-N-G-I-T-U-D-I-N-A-L. This is a transverse wave where the back and forth or to and fro motion of a particle of the medium is perpendicular to the direction of propagation. Transverse. This is a longitudinal wave. It's in the same medium, the slinky, but the back and forth or to and fro-ingness, the to and fro motion of a particle of the medium is along the same direction as the direction of propagation. Longitudinal waves have something that's parallel. Transverse waves have something that's perpendicular. And I demonstrated both of those for you with the slinky. There are some classic examples in the world of transverse waves. The water waves at the beach are transverse waves. And light waves. We're not going to talk about light in AP Physics 1, but I hope you're going to take AP Physics 2, where we will talk in a lot of detail about light. And I will show you why light is a transverse wave. And I'll tell you what it is that's perpendicular to the direction of propagation, something to be excited about for next year. The classic example of a longitudinal wave is a sound wave. So as the sound travels through the air, the particles go back and forth, parallel and anti-parallel to the direction of propagation. And we will talk a lot about sound and longitudinal waves after the AP Physics exam, but still this year in AP Physics 1. All right, that is all I have for you today. That was our introduction to Unit 6 on waves and whatever magical thing this SHM stands for. We've covered a lot of vocabulary, and I did that beautiful example for you with the slinky. I hope you'll go back and forth and watch that again. Have a happy day. I look forward to seeing you very, very soon in class. Bye-bye.